Hey everybody, in this video we're going to talk about equivalent fractions and we'll be looking at some area models, some length models, and some equal shares word problems that you can use to help your students understand equivalent fractions. So the idea of equivalent fractions is that two fractions are considered equivalent or equal to each other if they represent the same amount. And so if we look at area models for the fractions 1/2, 2/4, and 4/8, we can see that these fractions are equivalent because they cover the same amount of area. And there's actually even more fractions than just these three that are equal to each other, but these are some examples of equivalent fractions. You can also use length models to help your students understand the idea of equivalent fractions. So in this case, I used fraction strips to show that 2/3 is equal to 20/30ths, which is equal to 10/15ths, which is equal to 6/9ths, which is equal to 4/6ths. And so this would be another example of how you can show your students that fractions with different numerators and different denominators can still be equal to each other because they represent the same amount. And in your textbook, they recommend using equal shares word problems to help students understand this. So let's say that at a birthday party, you have a group of 8 kids that's given 2 cakes to share, and another group of 4 kids is given 1 cake to share. And you could ask your students, if you want to eat the most cake, which table should you sit at? And your students might come up with something kind of like this, where they have 2 cakes for the one group that are each split up into 8 pieces, and each kid gets 2 of those pieces. So we would say that that's 2/8. And then the other group of kids has 1 cake that's split up equally into 4 pieces. And so this represents the fraction 1/4 because you're dividing 1 cake equally between 4 kids. And your students might look at this and say, well, like if we just took this piece of cake right here and moved it over here, then that would make up 1/4 of the cake. And so these two fractions are actually equal. It doesn't matter which table you sit at because you'd get the same amount of cake either way. And then once your students have solved some problems like this, you can look at the equivalent fractions that they found and ask them if they notice any patterns between these two fractions. And in this case, they may notice that there's a multiplicative relationship between the numerators and the denominators. Because if you multiply 1 times 2, you get the number 2. And if you multiply 4 by the number 2, you get the number 8. And they might start to notice that pattern. And this idea of multiplying the numerator and the denominator by the same thing is a key concept when you're finding equivalent fractions. So let's say that we were trying to find a fraction that was equivalent to 3/5, where the denominator of the equivalent fraction is 15. Well, what this is telling us is that in our new fraction that we're trying to find, we want to have 15 equal sized pieces within the whole. And so I'm going to use an area model to represent the whole, but you can also use a number line model, and I'll show you another example of that in a minute. Um, but if I have 3/5 and I want to have my circle split up into 15ths, that means that I'm going to need to cut these pieces into smaller pieces. And specifically, I'm going to cut each one of these fifths into thirds, or to cut them up into 3 equal sized pieces. Because if I have 5 groups of 3 of these smaller pieces, that's going to give me a total of 15 of the smaller pieces in the entire circle. And so essentially what I'm doing here is I'm multiplying 5 times 3 because I'm making 3 times more pieces in the entire circle. And then if we notice the numerator, which describes the shaded area, this number is going to have to change as well because before we just had 1, 2, 3/5. But when we split the fifths up into 15ths, it made it so we had a lot more pieces. And each one of these pieces that used to be fifths are now 3/15ths. And so we'll have 3 from this section, then 6 when we add these, and 9 from here. And so that's how we get 9 on the top. And notice that this is multiplying the top by 3 as well, because when you cut up all of the pieces into 3 equal smaller slices, it also cut up the shaded ones. And so this is the basic concept behind finding equivalent fractions. And you can follow this process for all sorts of different denominators. So for example, if I wanted to find a fraction that was equivalent to 3/5 that had a denominator of 30, rather than splitting up each of the pieces into 3 smaller pieces, I would actually want to divide them up into smaller pieces because 5 times 6 is 30. So if I split up each one of these slices into 6, I would have 6 and then 12. I'm sorry, these don't look exactly equal, but they could be. And then I would have 18 and 24 and 30 slices in the fraction or in the circle altogether. And the 3 pieces that were previously shaded are now 6 times as many slices because I cut up each one of them into 6 smaller pieces. And so 3 times 6 tells me that 3/5 is equal to 18/30. And you can also follow this pattern if you want to find equivalent fractions where you're given the numerator. So let's say I wanted to find a fraction that was equivalent to 3/5, but it has a numerator of 12. Well, to do this, you just notice that 3 times 4 equals 12, which means that I'm going to cut up each one of these pieces into fourths, which will give me a total of 12 shaded pieces because I'll have 4 from the first one, another 4 from the next one, which makes 8, and then another 4 from the next one, which makes 12 shaded pieces. But in order to make all the pieces in the circle the same size, I also need to cut these ones up into fourths. And that's where we would multiply the denominator by 4. Because if I take all 5 of the pieces in my circle and cut them up into 4 smaller pieces, then I'm going to have 20 of those smaller pieces. And so 3/5 equals 12/20. So this is how you can show students to find equivalent fractions using area models. And I use circles on all of these examples, but you could also use rectangles. And I'll have some examples in the answer key for your homework that show examples of how to do that. But I also want to show you guys how you can do this on a number line. So if we have the fraction 4/3 and we want to find an equivalent fraction that has a denominator of 21, the first thing to do is to show where 4/3 is on the number line. So we can go 1, 2, 3, 4/3 away from 0. So this point right here is equivalent to 4/3. And if I want to make it so the fraction has a denominator of 21, well, that basically means that I need to cut the space between 0 and 1 up into 21 pieces. And because 3 times 7 equals 21, one way I can do that is by splitting up the distance between 0 and 1/3 into 7 pieces, like this. So we have 1, 2, 3, 4, 5, 6, 7. And they should be equal. So sorry that mine weren't spaced correctly. And then you could do the same thing with all of the thirds. So I could take this third and split it up into 7 equal pieces, and take this one and split it up into 7 equal pieces, and this one, I think that's right. And when I do that, the distance from 0 to the point that we determined was 4/3 is going to be 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28 of these units of 1/21. And that makes sense because 4 times 7 equals 28. And so it's a similar idea to the area model where you're taking each piece and cutting it up into smaller pieces. But this is just a way of showing it in a length model, like a number line model, instead of using an area model. So I hope this video was helpful for you guys. If you have any questions, let me know, and I hope you have a great day.